Okay, so we have been studying polynomial rings over commutative rings, and we have seen quite a few things by now. So let us now consider a unique factorization domain R and consider the polynomial ring Rx, that is the polynomial ring in the indeterminate x over a unique factorization domain R. Our main aim in this video will be to prove that Rx is also a UFD, a unique factorization domain. So let's proceed by considering a UFD. Let R be a unique factorization domain. Now a UFD by definition is an integral domain, so it has its own field of quotients, which we already know. Being an integral domain, and that follows from that result, theorem 361. R has its field of quotients F. Now we already know from this theorem that we can consider, in fact, R can be embedded inside this field. So we can consider R to be a subring of this field or embedded in this field. So from that it follows that the polynomial ring Rx can be considered as a subring of the polynomial ring Fx. We can consider Rx to be a subring of Fx. For any non-zero polynomial Fx in Fx we can write Fx equal to f naught x divided by a, where f naught x is a polynomial in Rx and a is an element in R. The justification of this can be found in exercise 11. That means if we are considering any polynomial over the field of quotients of R, then such a polynomial can be written as a polynomial over R divided by some non-zero element of R. So we will see how this happens in exercise 11. Okay, now the point here is this. It is, now this fact we will immediately use. but now what we want to do is this. It is natural to ask for the relation in terms of reducibility and irreducibility of a polynomial in Rx when you can consider a polynomial, since Rx can be considered as a subring of Fx. So if you consider a polynomial in Rx, then that polynomial is also an element in Fx. So you can speak of the polynomials reducibility and irreducibility in Rx as well as in Fx. What is the relationship between these two notions? Or rather the notion of, say, reducibility in the two rings, are they related in any way? So we want to ask that question. Considered as a polynomial in Fx. And the next lemma answers this question. That is, if you consider a polynomial in Rx, then it is say a primitive polynomial, then it is reducible in Rx if and only if it is reducible in Fx, or equivalently it is irreducible in Rx if and only if it is irreducible as an element of Fx. So let's see the statement of the lemma. So this is lemma 3.11.4. If Fx in Rx is primitive, and irreducible, as an element of Rx, then it is irreducible as an element of Fx. And the converse is also true. Conversely, if the primitive polynomial Fx belonging to Rx, keep in mind that we have to choose Fx in Rx, because then it is also automatically an element of capital Fx. However, if you choose an element in capital Fx, then it's not necessary that that also is an element in Rx. The coefficients of that polynomial may not lie in R, but they may lie in the field of quotients f, which is larger than R in general. Okay, so this primitive element is irreducible as an element of fx. Then it is also irreducible as an element of Rx. So we are going to prove only one part, because there are two parts of this lemma, one implication and its converse. We will prove only one part here, and the converse will be treated in the exercises. So the proof is this. What we are going to do is this. We are going to, of course, consider a primitive polynomial fx in Rx, and we are going to consider that it's irreducible as an element in Rx but reducible as an element of fx, and then we will arrive at a contradiction. So this will prove the first half. The converse will be treated in the exercises. So suppose the primitive polynomial fx in Rx is irreducible as an element of Rx. But reducible as an element of fx. So because it is reducible as an element of fx, so it can be factorized in fx in a non-trivial manner. More precisely, by that we mean this. Then fx is equal to gx times hx for some gx and hx belonging to fx such that both gx and hx have positive degree. That means none of them is a scalar, or none of them is a constant polynomial. None of them has degree 0. Now we have already seen how for a given element in fx we can write it as an element in Rx divided by an element of R, and in exercise 11 we will see that we mentioned it. So using that fact, Gx and Hx are elements in fx, so we can write Gx equal to G naught x divided by A, and Hx is equal to H naught x divided by B, where G naught x and H naught x belong to Rx and A and B belong to R. We are yet to see why this happens, but we assume it to be true for now and we are using it. Okay, we will later on in the exercises we will see what is the justification for this kind of, for the existence of these things. But something more is also true. Since G naught x and H naught x are elements in Rx, so we can write G naught x equal to alpha times G1 x and H naught x equal to beta times H1 x, where alpha is the content of the polynomial G naught, just like that beta is the content of the polynomial H naught. And G1x and H1x are primitive polynomials in Rx. We have already seen this previously. The thing we have seen is that if we have a non-zero polynomial, then that non-zero polynomial can be uniquely written as a product of its content, which is the GCD of all the coefficients, and another polynomial which has content 1 or content a unit. I mean the uniqueness that I am saying here, that this factorization, you can call this one also a factorization of a polynomial as a product of its content and the other polynomial, is unique in the sense that it's unique up to associates, because we already know that if you take the content out, that means you are taking the GCD of all the coefficients out. GCD is not necessarily unique. We have already seen this previously in Euclidean rings also. They are not unique. So alpha, the content itself is not unique strictly speaking, but up to associates it's unique. If you take out one GCD, you multiply it by a unit and you multiply the other polynomial by the inverse of that unit, that will give you another factorization. However, they are not considered to be distinct. The point here is that we get one factorization, and this one is a primitive polynomial, that is a polynomial whose content is 1 or a unit in the underlying ring. Okay, so by that G naught and H naught have been written like this, where alpha and beta are contents of f naught and g naught and h naught respectively, and these are primitive polynomials in Rx. Hence, so what do we now get? Ultimately, fx is equal to g naught x divided by a times h. Let's just first write that. Divided by ab, and this further is equal to another expression which is in terms of alpha, beta, ab, g1 and h1. Now we can multiply on both sides by AB, so which implies AB fx is equal to alpha beta g1x times h1x. Now fx is given to be primitive. That's how we have chosen fx. g1x and h1x are primitive because that's how we have got g1 and h1. So their product is also primitive. We have already seen this previously. If we take the product of two primitive polynomials, then that is also a primitive polynomial. So we are going to use this fact, and the result is this lemma 3.11.3 by lemma 3.11 means in this section itself 3, this product g1x h1x is a primitive polynomial. So because this is a primitive polynomial, the content of this right hand side, because the right hand side after all is a polynomial, the content of that polynomial is alpha beta, and due to the primitivity of fx, the content of the polynomial on the left hand side is ab, and since the polynomials are equal, the contents are equal. You have to understand that in this context equality means up to associates. It's not necessary that literally AB is equal to alpha beta, but AB divided by alpha beta or alpha beta divided by AB is a unit, which may not be 1, but it does not matter. After all, it's a unit. So content of this polynomial right hand side g1x h1x is equal to alpha beta. Also due to the primitivity of fx, content of AB fx is equal to AB. Thus AB is equal to alpha beta, and this equation has to be understood in terms of that up to associates. Hence, we have, so what do we have from this equation? Fx equal to alpha beta divided by AB g1x h1x is equal to g1x h1x, where it seems like we have used the fact that alpha beta by AB is equal to 1. But even if you take a unit here, because only that much you can say that this ratio will be a unit, then also you can multiply one of these polynomials by that unit. It will continue to be a primitive polynomial. You think of why that is so. Okay, I'm not going to explain anything more on that. That is, if you multiply a primitive polynomial by a unit, then you still get a primitive polynomial. It has to do with the GCD, of course. The GCD of the original polynomial is a unit. What happens when you multiply all the coefficients by, say, another unit? The GCD of the resulting products, that is the coefficients of the resulting polynomial, is that also a unit? That is, yes, that is true. Why that is true, that is I leave it up to you to figure out. Okay, so we have now got this. Now let's just see for a moment what this means. Fx has been written as a product of two polynomials g1x and h1x. They are primitive polynomials, fine, but they are in Rx. So that means this is a factorization of fx in Rx. One more thing is that, looking at these equations, this g0x equal to alpha g1x and h0x equal to beta h1x, you can clearly see that the degrees of g1 and g0 are same, the degrees of h1 and h0 are same, and because g0 and h0 themselves are coming from g and h, both of which had positive degree, so the degrees of g0 and h0 are also positive, and they are coming in a similar manner. That is, we are dividing this thing by an element of R. Here also we are dividing this polynomial by an element of R, so the degrees don't change. The degree of gx is the same as the degree of g0, and the degree of g0 is the same as the degree of g1. So because this has positive degree, g1 also has positive degree, and similarly because hx has positive degree, h1x also has positive degree. So that means this is a non-trivial factorization of fx in Rx, which contradicts the hypothesis that we assumed fx to be irreducible in Rx. So that is a contradiction. Now, since let's just argue with gx. Gx is equal to g0x divided by a, and g0x is equal to alpha times g1x, where a and alpha are elements in R. We have degree of g1x is equal to degree of g0x and that is equal to degree of gx, which is positive. So g1x also is a polynomial of positive degree. Similarly, degree of h1x is also positive. But then fx equal to g1x h1x contradicts the hypothesis that fx is irreducible in capital Fx. Sorry, I mean in capital Rx. So our supposition that fx is reducible in fx is wrong. That means fx has to be irreducible over f or irreducible in fx as well. So this is one half of the proof. The other half we will see in exercise 12. Oh, and by the way, this part where we are arguing that these degrees are equal, this part I think it needs some extra explanation. Can we not just simply say that these degrees are like this? Okay, we will see. There is something that we need to say here. We cannot just simply argue that they are equal by what we already know. Apparently, I can't get the point why we cannot say that these things are equal. Do we not have this formula that degree of fx gx is equal to degree of fx plus degree of gx. We have considered R to be a UFD. So a UFD by definition is an integral domain, and in an integral domain is this formula not true? It should be true according to me. Okay, we will see when we deal with exercise 4. We will see what extra explanation, if any, we need to fully justify this part. So let's just add a portion here. Here after this, before ending the sentence, see exercise 4. Okay, so that means this one half of the proof is over. For a or let me write like this. We will prove the converse in exercise 12. So this completes the proof. I mean, it completes the part that we are showing currently. Okay, now after this, there is this natural next lemma. Lemma 3.11.5. If R is a unique factorization domain, and Px is a primitive polynomial. In Rx, then it can be factored in a unique way. As the product of irreducible elements in Rx. So this is again a unique factorization theorem, but only for primitive polynomials in Rx, not for all elements of Rx. Okay, note that carefully. Unique way as the product of irreducible polynomials in Rx. Okay, so let us see the proof. We will start by considering a primitive polynomial in Rx, and then we will try to factorize it. Let it's given. Px is a primitive polynomial that is given. Since Px can be considered as an element of fx, where f in the whole context of today's video, f denotes the field of quotients of the UFD R that we are considering in any lemma. Okay, so ideally I should have written where f is the field of quotients of R, but I am not writing that. You understand what it means. Since Px can be considered as an element of fx, so by lemma 395, you can factorize px as a product of irreducible polynomials in fx. Px can be written like this: p1x, p2x, etc. say pkx, where these are irreducible polynomials in fx. Now what is it that we have used here, and what is lemma 395? Let's recall that also. What we have done here is this: px is an element of rx, and rx can be considered as a subring of fx. So px is an element of fx, and we have already seen in section 3.9, where we started our study of polynomial rings, that when f is a field, fx is a Euclidean ring. So being a Euclidean ring, fx itself is a unique factorization domain. So any element in fx can be written uniquely as a product of irreducible elements in fx, that is irreducible polynomials. And this lemma 395 is just the unique factorization domain, that unique factorization theorem that we have in the section on Euclidean rings, adapted for the polynomial ring fx. So that is the statement, the fact that fx is a unique factorization domain, that is lemma 395. So because of that, we are able to write px as a product of irreducible polynomials, but in fx, not in rx. We don't know whether rx is UFD. In fact, that's what we are going to prove eventually. So we have got this much. So these are irreducible polynomials in fx. Okay, now whatever we did with fx in the previous proof, we are now going to do with all the pi's. Okay, now for all index crows are awake at this time. I don't know what is happening. Everything has changed. Weather has already changed, all for the worse, and the temperatures are also too much. So all the wild animals around, they are feeling everything, so they cannot sleep properly. At this hour, we should not have crows outside like this. Anyway, I am going off track. So for all indices, I lying between 1 and k, we have pix equal to, what should I write? Let's write fix. Okay, here I haven't written anything. Fix, just some hints I have, divided by ai, where you already understand what we are doing here. Fix belongs to Rx and ai belongs to R. Okay, so we have written all the pi's like this. Moreover, Fix itself can be written as Ci times, say, Qix, where Ci is the content of the polynomial Fi and Qix is a primitive polynomial in Rx. Okay, so we can write like this. Now each Qi is primitive, so we can use the fact that okay, so now you look at this equation. This equation means these two equations together. Using these two equations, what do we have? Pix equal to Ci divided by Ai times Qix. In fact, let's just write that. Now Pix is equal to Pix is equal to Ci divided by Ai, these are elements in the UFD R, times Qix, and this implies that because Pi is irreducible in Fx, Qi also has to be irreducible in Fx, because if we are able to factorize Qi as a product of two polynomials in Fx of positive degree, then clearly that also provides us with such a non-trivial factorization of Pix, contradicting the fact that Pix is irreducible in Fx. So Qix also has to be irreducible in Fx. So this equation implies that Qix is irreducible in Fx. Okay, owing to the irreducibility of Pix, that is understood. Now look at what Qix is. Qix is a polynomial for each I occurs, a polynomial in Rx that is primitive as well as irreducible in Fx. So by the previous lemma, each Qix should be irreducible over Rx also. That's what the previous lemma says. Hence, by lemma 3.11.4, is irreducible in Rx. Okay, but we haven't yet used these things in this factorization, so that's what we are going to do now. Now Px is equal to P1x, P2x, etc. Pkx this is equal to, let's use all the things. So this will be, see, let me just put some ink first. So this is C1, C2, Ck divided by A1, A2, Ak times Q1, Q2, Qk. Which implies Px is equal to C1, C2 up to Ck, Q1x, Q2x, etc. up to Qkx. Okay, now the way forward is just like what we previously did in the previous proof. Since these are primitive polynomials, so their product is also primitive. So is their product. And hence content of this also, since Px is primitive, the content of the left hand side is this product. Hence, these two contents are equal, in the sense of being associates. You have to understand that. And this implies, let's just write here, Px equal to So now we look at the final factorization. Px has been factorized like this, where these polynomials are now in Rx and they are irreducible. Okay. It seems like I have missed something, or no, so far I have not missed anything. So they are irreducible in Rx. Previously we had polynomials p1, p2, etc. They were irreducible in fx, but now we have got polynomials in Rx which are irreducible in Rx. So this is a factorization of px as a product of irreducible polynomials in Rx. So that means a factorization of a primitive polynomial like this exists. We now have to prove that this is unique. Okay, so that part is still there. But before we write that part down, let's just summarize what we have got so far. Note that each qix is we already know this, but just for showing that this is such a factorization that we were seeking, so we are writing this: irreducible in Rx. Now let us show the uniqueness by considering such a factorization and then showing that such a factorization is essentially unique, essentially the same as this one. Let px be equal to r1x, r2x, etc. to rmx. It's not necessary that we will have the same number of irreducible factors. That is also not necessary. We have to show that we have the same number. M may or may not be equal to k. This, where are irreducible polynomials in Rx. Okay, now because the left hand side is primitive, each polynomial on the right hand side also has to be primitive, because if one of them is not primitive, then its content will be a non-unit that will contribute to the content of the product, and so the content of the product will also be a non-unit, and that would contradict the fact that these two polynomials are equal. On one side you have a polynomial of content that is unit, that is equal to a polynomial which is a polynomial of content non-unit. That is not possible. So that's why, since px is primitive, each Rix is primitive as well. Okay, so these are primitive polynomials that are also irreducible in Rx. But by the previous lemma, three, 11, 4, then these are also irreducible over fx, where f is the field of quotients of R. Yes. Each Rix is irreducible in fx. So these two factorizations of px now also can be viewed as factorizations of px in fx, because after all the polynomials that we see here are elements in fx also. Fx is the larger polynomial ring, and we already know that any such factorization of a polynomial as irreducible polynomials in fx is unique up to associates, because fx is a unique factorization domain. Being a Euclidean ring, fx is a UFD. So from there we will get the uniqueness part. So by lemma 395, m is equal to k and the Rix are equal to the Qix, where equality is up to associates. Taken in some order. It's not necessary that the order in which they have been written also is the it sets the correspondence that Qix is associated to R1, Q1x is associated to R1x, Q2x is associated to R2x. That's not necessary. There will be some ordering of these Ri's such that once you do that, then there will be an association taken in some order. Thus, or this proves that the factorization of px as a product of irreducible elements of Rx is unique. So this completes the proof of this lemma. Now we have all the tools that we can prove that if we start with a UFD R, then the polynomial ring Rx is also a UFD. We are now going to go to that result. That is the main result. It's theorem 3.11.1. In fact, I think I can state it here itself. If R is a unique factorization domain, then so is Rx. Oh, I was writing solution. This is proof. So we have to prove that an arbitrary non-zero element can be so factorized. Okay, so an arbitrary non-zero element. Okay. So let fx be an arbitrary non-zero element in Rx. Then we can write fx uniquely as fx equal to c times f1x, where this we already know, we have used this twice in this video, where c is the content of f and f1x is a primitive polynomial in Rx. Now, by the previous lemma, this primitive polynomial f1x can be factorized as a product of irreducible polynomials in Rx in a unique way. We have to still figure out what happens to this c, which is an element in R. Okay. By lemma 3.11.5, f1x can be uniquely written as a product of irreducible elements in Rx. Say we have a factorization of this element in R, that is the content of the polynomial f, as a product of elements in Rx. We will then try to figure out what such elements will be, or I mean, let's just see. Now that is what their properties are. Let C be written as a product of, because C, after all, you see, C is an element in R, so it's also an element in Rx. Now if we write C as a product of polynomials in Rx, say Amx, where these are polynomials in Rx, then since C is a constant polynomial, so its degree is 0, which is equal to the degree of these polynomials, and which we know is the sum of the degrees of the individual polynomials. A1x plus degree of A2x I think in the towards the end of the proof of the first lemma that we did today, that reference to exercise 4 that we are saying, it's not about that this degree formula is not true. It is true here, but I'm missing something else there which is needed, which we will see when we deal with exercise 4. That has been going on in my mind. Anyway, so now this is equal to this plus the last term is degree of Amx. Now degree by definition is a non-negative integer, and a number of such non-negative integers come together and their sum is equal to 0. So each one of them has to be equal to 0, which implies degree of, or let's just write that each AIX has degree 0, or in other words, each AIX is an element in R. So that means if we consider factorization of C as an element in Rx, then such a factorization turns out to be a factorization of C as an element in, as a product of elements in R itself. So when you consider possible factorizations of C, it's enough to consider those factorizations that have been done or considered in R, okay, because they are the only ones available. If we try to find a factorization in the general bigger ring Rx, of which R is a part, then that turns out to be again a factorization in R. And the exact language is this to express this. So the only factorizations of C as a product of elements in Rx are those the only factorization of C as a product of elements in Rx are those as products of elements in Rx are those as products of elements in R. In particular, every irreducible element in R is also irreducible in Rx. So that means if those factorizations of C that we are considering, if they tell us that a particular element in R is irreducible as an element of R, then as an element of Rx also it is irreducible, because you are not going to get any new factorizations by considering non-constant polynomials that may help us factorize this constant C. Okay, and the consequence of all these things is this: since R is a unique factorization domain, because that's how we started the things, right? R is a UFD. C has, or C is, C can be uniquely written as a product of irreducible elements in R. So let us just summarize what we have got so far. We started with a non-zero polynomial fx in Rx. This polynomial is uniquely expressible in this form. Where this is an element in R and this is a primitive polynomial in Rx. Okay. Now this is, this can be written, this f1x can be written uniquely as a product of irreducible elements in Rx. Fine. Since C is an element of R and R is a unique factorization domain, C also can be written as a product of irreducible elements of R in a unique way, but we had to make sure that C does not have any other factorizations in the larger ring Rx, because the uniqueness of factorization of C within R is there, but in the larger system we really none of these two parts tells us that C cannot be written as a product of irreducible polynomials in Rx in a possibly different way than, say here, in a different way than, say, a factorization like this, where these are all elements of R. It may happen that C has some other factorization also as irreducible elements in Rx which are not necessarily in R. Non-constant polynomials. Polynomials are positive degree. In this part we have shown, or rather there we have shown that if you consider any such factorization, then all of these polynomials turn out to be constant polynomials. So that means whatever we are considering here within R is what we have. Okay, so if C is an element that can be factored in only this way in R, then in the larger system also this is the only way in which C can be factored. The more added things, that is the other non-constant polynomials that are coming from outside of R, they don't help us give any new factorization of C. So now f1x originally is factorizable uniquely as a product of irreducible elements of Rx. Now C also in the larger system is factorizable uniquely as a product of irreducible elements in Rx, because you see every irreducible element in R is also irreducible in Rx. So if this is a factorization of C as a product of irreducible elements in R, then these are also irreducible in Rx, and together these two factorizations give us a unique factorization of fx as a product of irreducible elements in Rx. These elements along with the elements that appear in the factorization of f1x. So that is our conclusion, and we are now going to write. The unique factorization of C as a product of irreducible elements of R and hence of Rx, a factorization of, say, this. And the unique factorization of f1x as a product of irreducible elements of Rx. Say f1 is expressible in this form: p1x, p2x, etc. say pkx. These are irreducible elements in Rx. These are also irreducible elements in Rx. Then you just write them here in place of C and F1x. So that will be a factorization of Fx as a product of irreducible elements in Rx, which is unique also. So these two things give us a unique factorization of Fx as a product of irreducible elements in Rx. So that's what we just wanted to show. So this completes the proof. That means if R is an is a unique factorization domain, then Rx is also a unique factorization domain. And now clearly we can extend this to any finite number of variables, because then you can consider another variable, say y. Then this is a UFD, so Rx comma y, that ring in two variables, that polynomial ring, that will also be a UFD, and so on. So we naturally have this corollary about which I am not going to give any more explanation. I will just simply write, if R is a unique factorization domain, then so is this multivariate polynomial ring. Okay, you just have to apply the previous theorem a number of times. So we get this non-trivial result. If a polynomial in such a ring is given, it may be extremely difficult to find the factors of that polynomial in this ring which are irreducible, and hence to write the factorization, such a factorization. But we at least know that such a factorization always exists, and it is unique up to associates, which, given the complexity of the objects in such a ring, is not a trivial result at all. And we of course have this special case of this corollary 1. If F is a field, then this polynomial ring is a unique factorization domain. Where we have simply taken F in place of R. The question is, can we do that? Of course we can do, but exactly how? Let's just see that and end this video. R is a unique factorization domain. In its place we have taken a field. Is a field a unique factorization domain? Yes, it is, because every field is a Euclidean ring. What is the D function? The D function simply is this. D function is defined on all the non-zero elements in the ring, and it's a an integer valued function, what you do, I think I have discussed about this before also. You define the d value of every element in f to be equal to the integer 1. You will notice that this turns f into a Euclidean ring, and because every Euclidean ring is a unique factorization domain, so f is also a unique factorization domain. So in place of r we can take f, and this ring and its field of quotients, which is the field of rational functions in these variables over f, we have already discussed. These are important objects of study in algebraic geometry. So here this section ends, and this was the last section. Ends means we still have the exercises to solve. So in the next part we will do just that. We will solve the exercises, and after the exercises are over, we will then attempt the supplementary exercises also. So let's see how far we can go. And once ring theory is over, we will start vector spaces from topics in algebra. So if you have any doubt regarding this thing or any other matter regarding mathematics and related subjects, we can discuss in the comment section. Some of you are actually doing that, so thank you for doing that. So I end the video here itself. Signing off for tonight. This is me, Lucifer from hell. I was saying hell. It is hell in a sense, but it's a mathematical room. Have a nice night.